Hi, welcome back to my channel. Well, this is a video which is in continuation to the previous video which was made on chi-square test for goodness of fit. But there are some circumstances when we have an independent number of observations which belong to a random variable where the attributes are classified into two categories. One attribute belongs to rows and another attribute belongs to columns. Or we have a situation where we have to test the dependence or the independence of two attributes, two qualitative variables, or rather we can say where we are interested to seek a certain kind of association that exists between two qualitative variables. And the important thing, or in context of testing of hypothesis, we can say where we are interested to test the independence or dependence between two qualitative attributes. For that we usually use chi-square test for independence. For that we have a problem here, rather an example which we want to solve in the spreadsheet of MS Excel. So we have some data set here, and this belongs to 1000 trees of cherry orchard, and we have to test whether the yielding capacity, which is one of the attributes of shaded and unshaded, if unshaded trees, or we can say the another attribute is shading effect of cherry orchard, differ significantly. And the null hypothesis here is that the yielding capacity and shading effect of cherry orchard are not associated. That means there is no association between these two attributes, or we can say both these attributes are independent of each other. So out of 1350 belong to this high yielding and shaded, 205 belongs to high yielding again but unshaded, and similarly rest of the two cells which belong to yielding low yielding trees, but they have been classified into shaded as well as unshaded. So in order to calculate the chi-square in case of MS Excel, for testing the independence of attributes, the important formula for that is, that means we can directly get the chi-square. For that we need to get the grand totals and row total, column total. Since this kind of data set which is in the form of rows and columns, in terms of chi-square we used to call it as contingency table, or in a contingency form. Contingency form means the data is arranged into rows and columns. Here the rows belongs to the yielding capacity and the columns belong to the shading effect. For that we can use this direct formula, or we can use this formula, expected frequency, because these are the observed frequencies and we need to get the expected frequencies also. For that we'll be using this formula, row total into column total divided by grand total. That means if we want to get the expected frequency of this cell, for that I need to first calculate the row total of its row total and its column total and then its grand total, which is quite simple. I will simply highlight all these values including these blank cells. I will press on Alt and plus. So we have grand total, we have row total for first row, row total for second row, similarly column total for first column, column total for second column. Then we can directly put these values in this formula and we can get the chi-square. But another way of doing this kind of analysis is to get the expected frequencies, which I recommend. So in order to get the expected frequencies, I will simply use this formula is equal to its first row total multiply by its column total whole divided by this 1000, which is grand total. So we have got the expected frequency of the first cell. Similarly row total, since it belongs to the first row, multiply by its its column total, then whole divided by 1000, enter. Similarly is equal to row total but second one multiply by its column total whole divided by this 1000. Then in order to get this, again the row total will remain same, only the column total will change, whole divided by this constant value of grand total. So we have got the expected frequencies. For that let's solve this thing in this here we have to put all these observed values in this fashion. Let us control copy. I will put all these values here, transpose, then we have another value for the second row, control C. Okay, then I will use this option again, transpose option. So we have this thing, and here control C and put them in the expected one, but here what I have to do, I will click on values also, then transpose. Okay, then similarly we'll do the same thing for the next two cells. So simply is equal to observed minus expected, enter, then we will drag these values up to here, minus 17 for all. Then what we will do, we'll do the squaring of all these values like this. We'll put them in curly in brackets and raised to power 2, enter, remains constant. Then we will use this formula, this divided by the expected frequencies, press enter, then drag up to this and simply get the sum is equal to sum. Press enter. So we have a chi-square value, which is rather a calculated chi-square value is 4.875, and the degrees of freedom here is 1, because we have 2 rows and 2 columns, and to get the degrees of freedom for a chi-square for in case of independence testing, or we can say chi-square for test for independence, we have we can get the degrees of freedom by multiplying two things, row minus 1, column minus 1. That means r minus 1 into c minus 1. So here the degrees of freedom is 1. So in order to get its tabulated value, we will simply use this function chi inv. So here let us suppose I will write it as chi cal. That means this is our calculated value, this one. I will highlight this. Now I need to get this tabulated value. I will write chi tab. For that I will use chi inv function. Chi inv function. For that, the probability value, say for example, I will choose the 0.01, 0.05, sorry, and the degrees of freedom is 1. Then here you can see the calculated value of chi-square is greater than its tabulated value, and in case of testing of hypothesis, the thumb rule is whenever the calculated value of any test of significance is greater than its tabulated value, then we have got a clear-cut evidence to reject the null hypothesis. The null hypothesis here was that both these attributes are independent of each other, but we have got evidence due to this high value of calculated chi-square. So both these attributes are not independent of each other, rather there exists a certain kind of association, which can also be verified from the p-value chi dst is equal to chi dstr. Here the chi-square value for the calculated one is this, and the degrees of freedom is 1. So here the actual p-value is 0.02, which is quite low than the standard 0.05, and when we are testing the hypothesis in context of the p-values, whenever the p-value is less than, if the standard is 0.05, whenever the p-value is less than 0.5, that means we can reject a certain kind of a null hypothesis. So in both these cases, as far as p-value, or rather we can say this calculated and tabulated value. In both these cases, this null hypothesis is to be rejected. So the hypothesis that was yielding capacity and shading effect of cherry orchards are not associated is rejected by means of this, the value of chi-square, which is calculated 4.8, which is greater than this, and as far as this chi-inv as well as chi dst, or in context of p values, in both these situations we can reject the hypothesis. But let me first cross verify it again by using this dist function, this chi-sq test. Let us check it again. Since this is our actual range, comma, this is our expected, then let's put enter. So again the p values are 0.02 and here also 0.02. Since this p value is less than the standard p value, that is 0.05, that means we have got an evidence to reject this hypothesis. So we can say the yielding capacity and shading effect of a cherry orchard in this example are associated. So the yielding capacity has a certain kind of dependence with the shading effect. So in this scenario we can say both these attributes are having a certain kind of association, or they are dependent on each other. So whenever we are interested to test the association or the dependence between the qualitative attributes, for that we need to apply chi-square test for independence. And whenever we are interested to test to determine whether observed frequencies are in agreement with the expected frequency, for that we need to apply chi-square test, which is known as chi-square test for goodness of fit. So this chi-square can be used for these two aspects. Hope you like this video. If you have any questions or comments, please post on the comment section below. Thank you.